question is about the finding equivalent resistance and the power, as I had clearly mentioned. But I will explain you not only that but also the fundamental concept that is required to solve the question. Now, so you see that I'm showing you the before cutting the wire. So there's a wire which have a resistance R. So let's say this is a resistance R that is connected over here, okay? And it is connected with a battery of EMF E, right, which is constant. So we will bring some change in the resistance, but we will not change the EMF of a circuit. Okay, so what we will do, our resistance of wire, the wire is in the form of cylindrical wire, right? So what we will do, we will cut the wire into the two pieces of equal length and then connect them in parallel, and then we will find out that what will be the power delivered or what will be the power dissipated in the circuit. Okay, so first of all, the wire is in the form of cylindrical, right? So just imagine this is a wire, okay? And when this is a cylindrical, it means that it have a certain cross-sectional area. All right, so that I'm going to show you now. And that is the circular cross-sectional area. All right. And this is a cross-sectional area, let's say A, and its length is L. So when you have cut the wire into the two pieces, by doing that, the material of the wire has not changed. So in the fundamental concepts, right, I want to tell you that the resistivity of the wire only depends on the material of the resistor. So which means that the resistivity will be constant still. So you know that the resistance of a wire is equals to the resistivity length over cross-sectional area. So when you will cut this wire from the middle, from the half, during this, the cross-sectional area will also remain same of those the small pieces. So which means that the resistance is only proportional to length. So let's say when you will cut the wire into the two pieces. So now these are the two individual pieces which have a same cross-sectional area, but since the length is just half, so L over 2 and L over 2. On this basis, we can say their resistance is also halved, so opposition in the flow of current will be halved. So now in this circuit, in the next circuit, I mean, when after the modification, this is the same EMF. So here I'm going to connect the resistance, the one half, you know, its resistance is R over 2, and we will connect here and other according to the guideline of the question, that this should be also R over 2. So in this new circuit, you have to find out the power dissipated in a circuit. But before that, since we need to compare the power dissipation, so what is a power dissipation in the original circuit? So this is a direction of current flow, right? So the power dissipated across the resistance can be written as I square R. It can also be written as V square over R, but the V is the potential difference across resistance, although it is equals to EMF, right? So whatever equation is good or convenient for you, you can apply that. Okay. Now, what we will do for this circuit, first of all, we need to calculate what is their parallel. Okay. So the parallel will be R over 4. I can tell you without calculation, because I told you that if the two resistances are identical, you can just half them. Okay. So this is now more simplified circuit. And here we have the total equivalent of the two resistances, which you can apply this equation because most of the students are familiar with this equation, 1 over R1. So that is R over 2 plus 1 over R over 2. Okay, so that will be 2 over R plus 2 over R. So it can be written as 2 plus 2, 4 over R, right? So I had already told you by the trig method that it would be equals to R over 4. Okay, so if the two resistances are identical and they are connected in parallel, just like you see here, you can just half the one resistance. Since it's R over 2, you can make it half, that is R over 4, right? It is 100% right. So this is a R over 4. Now in the original circuit, you can say it is E square over R. Okay, now dear students, you see that the two resistances were in parallel, so the potential difference on across them is E. Okay, so when I will try to find out the power dissipated, the new power dissipated, so can we say E square over R equivalent. So that should be equals to E square over R over 4. So that should be 4 into E square over R. So what is E square over R? You know that that is the power dissipated in the original circuit. So what we had calculated, now the power dissipated will be 4 times of P, and it is conceptually can be justified because you have seen that the resistance has reduced from R to R over 4. Just imagine if the resistance is reduced from R to R over 4, the current of a circuit will increase from I to 4I. Okay, so you know that the power is equals to I square R. So on a one side, where do you say that the resistance is reduced to R over 4? So the current is increased by 4 times. So its square will be 16I square. Clear? So once again, we get the same thing, right? Which means it is this. So power dissipated has increased by 4 times. So this is the answer for this question.